Hello, this is Ken, your CLES group leader for the Physics 2 course you're taking now with Dr. Baumeister. You ended up last quarter, Physics 1, with a study of rotational kinematics. And let's maybe just for a refresher, go over the analog between the translational motion and a rotational. For position, we had x and theta for velocity, v and omega for angular velocity, and acceleration, a and alpha. Now, try that again. The translational and rotational quantities are related to each other in this way. A tangential and the radial or centripetal acceleration, that. In the event that the accelerations are constant, acceleration, you will remember these. By the way, this is kinematics. Yes. So translational, the three equations of motion for constant acceleration. From Physics 1, I suppose. And the third one, not quite fundamental, but it's usually included anyway. And here too. So it's a theta. So much for kinematics. For dynamics then, first we'll measure of a body's rotational inertia. We have the moment of inertia. For rotational motion. And for translational motion, the very familiar mass M. And so what causes translational motion? You know, forces, the sum of the forces, Newton's second law, causes acceleration. The analog to that for rotational motion is the sum of the torques on an object equals its moment of inertia, rather, time its angular acceleration, where the moment of inertia is given in terms of the mass, r being the distance from the axis of rotation. Oops, back. Well, there. And the torque on an object caused by a force is given by this cross product. So we want to really use this Newton's second law. That will be the most important first equation that we'll be using here. Sum of the torques equals I alpha. Let's apply that then to a problem from the text, number 10.9. 10.9 reads, the flywheel of an engine has moment of inertia, 2, about its rotational axis. What constant torque is required to bring it up to an angular speed of 450 revolutions per minute in 7.9 seconds, starting from rest? So we write all of this information out. What do we have here? Write out in math what they give us here in words as best we can. Angular velocity, 450 revolutions per minute, a little unconventional, but, and the time, 7.9 seconds. I'm keeping the quantities without the units are in MKS units. So the 7.9 is 7.9 seconds. Initial angular velocity being 0, and the question is, what is the torque? We're given that the torque, which is the only torque, is I alpha. Oops. Try that again. So if the torque is a constant, the moment of inertia is certainly a constant, then the angular acceleration is a constant, and we can go to the angular acceleration constant equations, which one we want to use. We are not given the angular displacement, so looks like the one that we're going to use, and we are given the time, so this is probably the one, so that the angular acceleration is omega over t. And the torque then we're looking for, that will be I alpha I omega over T. And what is omega? But it's given here in radians per minute. We'll need to change that to radians per second in KS units for rotational velocity. Minutes. And what do we have there? When we cancel things out, it gives us a 900 pi over 60. Well, exactly 15 pi. Installing that then down here for our torque, and with a moment of inertia, 2 times 7.9. What is that? 30 pi over 7.9 newtons meter. Oh, now what is that? Approximately. So 11.93 newtons meter. All right. Well, next time we'll look at more rotational dynamics, rotational energies next time. Stay safe till then.